Good day. My name is Michael Gardner, and I'm here with my colleagues Xiaoming Wang and Godji Fortil. Together, we are going to be going over the HPCC platform clouds builds and our current deployment pipeline and workflow. The following subtopics will be covered. I will be giving an overview of the Docker image builds. My colleague Xiaoming Wang will be giving an overview of the customized Docker image builds. And my colleague Godji Fortil will be discussing how to do Terraform interactive deployments, as well as continuous integration using Terraform. So the first thing that I'm going to speak to you about today is our containerized builds. I'm going to give you a general outline of what they are, how they work, and how they work within our own development pipeline. So the first question that we're going to ask is, what is the platform core image? This is our primary image, which contains all the necessary libraries and executables for the HPCC platform. This has everything that you need to run the platform in both a single node configuration or for an entire cluster. This image utilizes a secondary image called the platform build image. This platform build image contains all the necessary dependencies for generating the platform core image, and it's where the end artifacts of our builds are located. You can then fetch and use these images within containers for your own systems. It is useful in pushing out Helm or Terraform deployments, or for testing locally on your own machine. The great thing about using Docker image builds is that the build environments utilized by both yourself and your colleagues on separate hardware are exactly the same. This is because the Docker file available on our HPCC platform GitHub repository contains all the definitions of what the build environment and final platform core container should look like. So let me go over how the platform core build works. First off, you have the layering of the Docker builds. Each Docker file has specific steps which define what the final image will be. The base of our build is the platform build image. As I said before, this is all the build dependencies that you and your colleagues will need to build the HPCC platform. Nested on top of this, we have the platform core image. It pulls libraries and executables generated from the platform build image and creates a final environment where the runtime dependencies are properly installed and the file structures are set up as one would expect in an HPCC platform runtime environment. Other builds are available, which layer on top of the platform build image, such as ML, GNN, GNN+GPU builds. So where is the build code located? It's all controlled through code. So if you look at our HPCC platform repository, you will see a Docker file directory located in any 8.x branch. These are all our Docker files for image generation, as well as helper scripts that I'll go over quickly. We have our buildall.sh script, which is used in GitHub Actions to generate our official builds. We have an incr.sh script, which is useful for development. This script will allow you to generate your own personal images called incremental builds, containing code changes that you've committed to the platform. These images are extremely useful for when a developer wants to quickly build and test changes. The image on the right contains a brief summary of the Docker file directory structure. Each Docker file has its own corresponding directory for its specific build layer. So what does the HPCC platform build workflow actually look like? First, everything is done as code. Our Docker file directory in branches 8.x and higher contain everything necessary to build the images. GitHub Actions workflows are then utilized to generate these containerized builds and then deploy these images to places developers can access them, such as Docker Hub. This is all kicked off by tagging a branch in the HPC Systems HPCC platform GitHub directory repository. Apologies. In the image on the right, you can see that Richard Chapman has tagged and pushed community 8.8.6-1. That's a gold release, and this causes GitHub Actions to generate all the images I showed you in the previous slide. This is done through the build and publish YAML script. The script has a list of instructions to call each Docker file with specific flags passed through. This allows us to build multiple images in parallel, such as our community, ML, GNN, and GNN-GPU builds. These are then pushed to Docker Hub. Docker Hub is used as a public repository for all of our community-facing builds. There you can find our ML, GNN, GNN-GPU, and platform core images. They are freely available, so please feel free to go peruse the repository and download whatever you like. The end user can now pull the generated images down to their local machines using a Docker pull command, and it's ready to be utilized within a container. So a little bit more about Docker Hub and what we push there. This is all for our public repositories. It contains our platform build image, which has all the build artifacts for each tag we've ever done on the repository. This is helpful if you need to go back and check differences between build artifacts, as you can easily fetch multiple build images and compare them. Then we have our final images, which are meant to be used in runtime containers. These are platform core, platform ML, platform GNN, and platform GNN+GPU. A quick note regarding the tags on Docker Hub. If you go to the Docker Hub HPC Systems repository, you'll see a latest tag for each image. That latest tag corresponds to the most recent and highest versioned gold release. This means whenever you pull the HPC Systems Platform Core latest tag, you will be getting the latest and greatest features we've implemented into the platform to date. Release candidates are also available on Docker Hub, but they'll never be using the latest tag. So if you want to test patches or upcoming features, please look explicitly for the release candidates on the images tab and be sure to pull those. So I'm going to give you a quick overview of how to build your own platform core container. This utilizes the incremental build script called incr.sh to create a development container. The first thing that you're going to want to do is to take your changes to HPCC platform source code and bundle them into a commit. Then you're going to push that commit to your forked HPCC Systems platform repository up on GitHub. Now we can run the Docker files -incr.sh script. We're going to pass the following parameters to it. -u and your GitHub username. This ensures that you're actually pulling from your repository to get your source code changes. -in and a custom tag name. I often find that it's useful to make the tag name self-documenting. I'll put in the name of the JIRA I'm working on or a brief description of the bug I'm fixing. This allows me to quickly differentiate the many different HPC platform images on my personal machine. This script will then generate a build environment, generate the build artifacts, create a platform core image that you can then use to test your changes. Docker image should now be visible using the Docker images command. So in summary, we have completely incorporated our build and development workflow for containerized builds as code. This code can be found in our public repository located at HPCC Systems-HPCC-Platform.git. We utilize GitHub Actions to run our Docker builds, and we have deployed the final images to Docker Hub for your convenience. I'm now going to pass the presentation off to my colleague, Xiaoming Wang.
Hi, my name is Xiaoming Wang. I will talk about the user HPCC Docker image. Just like Michael mentioned, we published several Docker image in GitHub, the Docker Hub. But all of this image actually is run only by user HPCC. So you can basically switch the root user to install any new package when you deploy it. So if you want your customer custom image, you need to build it. So basically, what you need to do is there are several steps. I show on the right side is the Docker files. Usually, you want to build your own one. So the first two lines is the parameter you pass to the Docker files. And then the third line as code is the base image. That really is what you want to base on. Normally, you will probably want to use the platform core. That is our main Docker image. And then the second line, the next line is that you need to switch from the HPC user to root user. And the next section is really what you want to put into your package and your Docker image. So all the package you want to add on top of the base image. So at the end, you need to switch back to the HPC user. So we only run HPC user to protect our image. So how you run is just run the Docker image build command with the -t, that is your tag, and then you pass the two parameters. First one is the repo, the Docker repo. That's normally it's HPCC Systems, and then your version you want to pick for the HPC Docker image. Now you need to run this command normally in the your directory that have a Docker files. Otherwise, you need to provide a link. So here is I have a dot. That means I'm on my local on the directory of the Docker file. So the command will find your Docker file automatically. The right side, the Docker file. Sorry. The right side I show the Docker file really is for our machine learning package. That's the we call platform -ml. Here is another example that is we build for the GNN support. So the basic structure is same. You pass two parameters, and then you have a base, and then you switch the root user, and then you add all the package you want. So this is we added package for support GNN. So mainly is for the TensorFlow and some other required softwares. At the end, you switch to the HPC users. So the next what I want to talk is about our GPU support. So basically how you can build your GPU Docker image. In Azure, basically the old VM type with GPU support start with letter capital N, and at least the types I can find now. I also listed two examples, two card examples. And the first one is a little cheaper, the T4. Another one is a V100, that is a little bit expensive. And with each card, there are several configurations you can choose. Basically, it's just a CPU resource memory and how many GPU cards. On the right side, I show the price. So normally the GPU image, I mean the VM is the expensive than your normal the VM. So you can see at the top, at least the normal one probably just about 38 cents per hour. And then even the cheapest GPU card, you probably get, let's see, the cheapest one is 50 cents per hour. And then at the bottom, you can see it's almost 10 times expensive than the normal price. So normally, if you just want to play with GPU support, you can choose the simple card. That's the cheapest one with the 4 CPU, 28 gig memory, and then 128 disk, and there's one GPU card. That's probably it costs about 50 cents per hour. So the related software is the one is the kernel mode driver. That basically was installed by the AKS to your nodes. And what we want basically is the CUDA toolkits and also TensorFlow. So we basically will add these two package to our Docker image. To be sure it is compatible with the NVIDIA kernel mode driver on your current AKS node. So we will build on our HPCC Docker image. Currently is the CUDA 11.04, or maybe the latest TensorFlow. For detailed compatibility reference, you can reference the link at least here. So how you verify, oh, sorry, I think I missed one. Okay, here. how you build your image is the currently we publish the GNN GPU Docker image. The source file we push there is the platform, and then Docker files, platform, GNN and GPU, and then Docker file. We build this one based on the TensorFlow GPU support Docker file. I have a link here. Actually, that is the one we currently reference. And also you can reference our README that in the same directory, there's a README file that tell how we build this Docker image. A note is for the future or other GPU cloud environment, you may need to build your own GPUs supported Docker image. For example, you may have a new CUDA version for support the kernel mode driver or some other compatibility concerns. So now you have your Docker image to support GPUs, how you test it. There are two options. First one, you can deploy your HPCC cluster either from the Terraform or maybe the Helm, or you can simply just deploy the one part with the YAML file, at least at the right side. That is the for the Azure environment. So you can see the Azure resource to support GPU. That's the syntax you should put there. And then you can use the kubectl exec command to log into the bash. And then you can run the command is the nvcc. So that will tell you the version about the your kernel drive card, driver. Or you can run the actually this is wrong, sorry. So it basically is the nvida-smi, and this will actually print out both your kernel driver and your CUDA versions. And then the next, you can run the Python 3 interpreter, and then you can run several commands. You can import the TensorFlow, and they can print to test if GPU is available. And then you can run a simple command to run some exercise to make sure the calculation is using GPU card. That's all I'm talking about for today's topic. Basically, it's covered how you build your custom Docker image, and also how you build your GPU supported Docker image and how you test it. So next, I will transfer my colleague Godji to talk about HPCC Terraform in action deployment.
Hi, thank you for joining us. I'm Godji, and today I would like to go over some of the improvements that we have made over the year on our Terraform HPCC module, and some of the features that are coming very soon. So what you are looking at is an overview of our module. What I want you to take away from this picture is that we have divided our module into 3 different independent modules. And the advantage of that is now we are able to deploy the AKS and destroy the AKS whenever we want without destroying our storage. So let's talk about some of the improvements that we have made. And by starting with the multiple storage accounts. Before, we had a single storage account, and all of the data planes were deployed within that storage account, which means that they share the same settings, the same access tiers, the same account tiers, and the replication type. Now we have multiple storage accounts, and the advantage of having that is that we are able to set one data plane per storage account, which means that we can now have DALI on a hot storage, for instance, while my drop zone can be on a cold storage, for instance. And with that comes big savings, because you no longer have to use, for instance, when you had a a single storage account where you wanted to use a premium storage, you no longer have to use the premium storage for all of the data planes. You can choose to have DALI and a separate storage account where you use the premium storage and have the rest of the data planes inside multiple or a single storage account of your choosing. So let's take a look on the old way we used to do that. So here, what you're looking at is an example of a single storage account where we have all of the settings and all of the data planes share the same storage account. Next, we have the new way of doing it. At the top level is this definition for the DALI storage account. And we can have multiple blocks of storage accounts, and each block represents the definition of a storage account. For instance, we can have DALI, we can have Sasha, we can have my drop zone. And at the bottom, we have the definition for the data plane within that storage account. So as you can see, we have a single data plane inside a single storage account. So we have the data plane definition, which includes the quota, the permissions, the access tier, and other settings for the data plane. And the subpath and category attributes are required by the HPCC platform. So those two keys must never be changed. So let's look at an example of if you had a storage account already created outside of the module and that you want to use that storage account with your deployment. So this is how we used to do it. We have the location, the name, and the resource group name. So let's take a look on how we do it now. So if you were to have storage accounts or as many as you have and you want to deploy them, we want to use them within your deployment. This is how you do it. You have the storage account definition on top with the name and the resource group name. And at the bottom, you have the definition for the data plane within that storage account. Next, let's talk about some of the upcoming features that we have, such as log analytics workspace, continuous integration, and high performance computing cache. So what is log analytics workspace? With log analytics workspace for HPCC, we are able to have a dedicated environment for log ingestion and retention, and being able to access those logs through Azure services such as Azure Insights and Dashboard. So the benefits of having a log analytics workspace is that we can retain the HPCC logs for a specified number of days. We can set access control permissions on those logs, or we can say who we want to have access to those logs. We can transform those logs before we ingest them into the workspace. And we can also isolate the HPCC components logs. What I mean by that is that we can have a workspace per HPCC component. We can have a workspace for WAXI, a workspace for Thor, for instance. And on each of those workspaces, we can set a number of permissions and also other settings such as retention period and also transformation before ingestions. So here's another view of how we define the workspace within our module. So you can turn it on and off if you'd like. You can enable or disable it. So you can set enable to true to enable the feature. And you give it a name, and you have other settings such as daily quota, internet ingestions enabled, and so on. Next, let's talk about continuous integration. So our continuous integration is done using GitHub Action. With continuous integration, we are able to HPCC platform developers are able to continuously test their code changes without having to do any difficult work into going into deploying the cluster and then run some jobs. Next, we are able to, ECL developers are able to automatically deploy HPCC in Azure upon triggering a set of ECL jobs. And last, we are able to destroy the HPCC cluster once all of the jobs or all of our tests are completed. To use the continuous integration, you will need some services from Azure. For instance, you will need a service principal and also a federated credential. With the service principal, it comes with the application, the client ID. It comes with a value, which is the client secret, and also a tenant ID. And with the federated credentials, you will need a GitHub organization name to create that. You'll need your GitHub repository name, and you'll need other settings such as environment, and also based on selection entry. Next, once you have the service principal and the federated credential, you are able to create the GitHub secrets. On the right-hand side is a picture of the different the various secrets that we have created with during our test. So as you can see, we have a secret for each of the values, such as the client ID, the tenant ID, and also server ID and object ID. So some tips before using that is that you will need a service principal to use the GitHub action. You cannot just use your IAM. You'll need the service principal to use that. And also, when you define the environment variables, as you can see on the right picture, you will need to use the keyword ARM as a prefix for each of them. And also notice that for the environment and also the client tenant ID and subscription ID, those are the same values that we use for our federated credentials. Next, file locations. So as far as the file goes, we have created a DevOps directory inside the module. So all of the CI implementation is done within that directory. So as you can see, we have the DevOps, and then we have Terraform, and then we have all of the some of the TF that we use, some of the TF files that we use for the CI. And those CF files are automatically copied over from the modules themselves, such as from the virtual network module, from the storage module, and the AKS module. And if you want to take a look at that implementation, you can open the tf-ci.yaml file to see how that is implemented. Next, let's talk about remote states. So for the CI to work properly, you will need to set up backend storage so that you can store your states, so that next time when you come to deploy, you will deploy from the same states that you deployed before. And that way, Terraform will know exactly what to do and where you left off. To do that, you'll need to manually create your storage container on Azure. And then you will need to to check the backend storage definition inside the versions.cf file for each of the modules. As you can see on the right picture with the keys, each of the key for each of the module is unique. So you have to make sure that they are unique because they're going to be stored at in the same place, in the same bucket. So at the bottom is another picture of the storage container that we created in Azure to store the files. As you can see, all of the CF states file are in the same location. Next, let's talk about our ECL job test. So to run a job, we have created a workspace for all of the ECL files. So once you put your file there, we have a set of validation. We configure inside the CI file, inside the configuration file for each of the ECL tests that we do. Currently, we only have simple tests just to make sure that the deployment was successful. And then at the bottom is a picture of how we configure the environment to run the test or the ECL jobs. For that, we use a Docker container using the HPCC Systems platform core image. To learn more about that, I would suggest you take a look at our implementation. And next, let's take a look at the pipeline itself and how it is, how the workflow works. So as you can see on the right-hand side, we have all of the steps that are taken by the CI once it is triggered. And the CI can be triggered by git push. So every time you make a change on your code, for instance, if you are an HPCC system developer and you are working on a set of features and you commit and push your code to your repo, you can have a set of tests to test whether you have working something that was already working. And that is the git push trigger. Next, you can manually trigger the CI if you want to. And also you can, the CI can be triggered by other external events as well. So we have so far seen how to use multiple storage accounts for HPCC systems that allow us to have better storage settings, better performance, and better cost savings, as well as how to create a log analytic workspace, which is a feature that is coming very soon. And also continuous integration for HPCC systems developers and as well as ECL developers. And another feature that is coming is high performance computing cache, which will allow which will embed our performance as well. So if you want to try the multiple storage account feature, which is available right now, you can go to our repo, which is at github.com/HPCC system/Terraform Azure HPCC and give it a try today. So thank you for coming and have a good day.